In last session, we discussed about differential amplifier and we derived its small signal gain of differential amplifier using two methods like half circuit method and superposition method. Okay, using two for differential amplifier having dissimilar MOSFET or non-identical MOSFET, we used superposition method. For identical half circuit symmetry is there, we will use half circuit analysis to find the small signal gain of a differential amplifier. And today's lecture we are going to discuss how we can improve that gain of the differential amplifier. In the last lecture we consider a differential amplifier with some load resistance and a so we consider a differential amplifier with a tail current ISS and two MOSFET M2, here it is M1, and we given some differential signal here VD, here it is VDD. If these two resistors are RD and if the two MOSFETs are identical with transconductance GM1 or GM itself, then we found that the gain of the amplifier AV equal to minus GM into RD. So next question, or in this section, we are going to discuss how we can improve this gain of the differential amplifier. For that, we will discuss basic three idea how we can improve. Actually, we are going to improve the load resistance to improve the gain of the differential amplifier. The same idea we discussed in common source amplifier, how we can improve gain of a common source amplifier. The same thing we will apply here, because if we consider the half symmetry of this amplifier, this is nothing but a common source amplifier, right? If we consider the half symmetry in this circuit, it is nothing but a, here it is V in 1 and we are taking output here it is VDD. This is nothing but a common source amplifier. I forgot to mark this one for N type, and here we will take the V out between these two terminals. Okay, so this differential amplifier nothing but it is a combination of common source amplifier. What are the method that we used to improve the gain of a common source amplifier that we can equally applicable to our differential amplifier, such as we can replace this RD using large value of resistors, such as that we discussed our current source load, current source load and diode connected load, and one more is there, the cascaded load, cascoded configuration. All are applicable in the case of this differential amplifier also. And we can also apply, we need to also discuss one more thing in this differential amplifier, that is how we can take the single-ended output without degrading the gain. If we take the single-ended output of this configuration or this circuit, we will get the gain only, that is output is here is only minus GM RD by 2 only, because for this MOSFET it is getting only half of the differential signal. So how we can resolve this one, that also we need to discuss, but that topic we will discuss along with our operational amplifier. So today's lecture we are going to discuss about what happened if we are giving a current source load to instead of RD or diode connected load, and how we can improve the gain using cascoded configuration. Okay, these are the material note for the same. And first we will start with the differential amplifier with a current source load. We know using a MOSFET we can implement a current source by giving a specific bias to the gate. A specific bias to the gate. A MOSFET with a fixed bias at a gate will act as a current source, and its equivalent resistance is nothing but the channel length modulation parameter or the R0. Okay, channel length modulation resistance itself. So in differential amplifier with current source, the circuit is exactly same as the normal differential amplifier, except the load, that RD, we will replace with the current source. Current source is nothing but a MOSFET with a fixed bias. And note that here it is PMOS. Okay, here it is PMOS. Okay, PMOS, and here it is NMOS. And the analysis of this one, that current source load, we can either do it using small signal analysis or simply using our half circuit symmetry. As per our textbook, we are just using half circuit symmetry. If this differential amplifier having half circuit symmetry, that means this left half and right half are identical. That means we need to choose M1, M2, M3, M4 such a way that M1 and M2 are identical, M3 and M4 are identical. So the transconductance of M1 and M2 must be equal, and the channel length modulation parameters must be equal, and all other terms also, the dimensions also equal. Okay, W by L also equal. So here also P MOSFETs also that condition must satisfy. So here we are choosing M1 M2 such that its transconductance parameter is GMN, and here the transconductance parameter is Gm of P, and the resistance here it is R0 of N, the N type MOSFET, here it is R0 of P. That's all. So the analysis is very simple. Because it's satisfying the half circuit symmetry, we will consider only one of the half, and we are writing an equivalent half circuit of that differential half pair. In that, we can replace our current source with its equivalent resistance. So we will replace that current source with the current source with equivalent resistance, which is equal to its RO value. Here it is ROP. Then this transistor having a transconductance of GMN, then this half circuit is nothing but a common source configuration whose gain is nothing but the gain is AV1 is minus GMN RON parallel to ROP, or V in V out 1 divided by V in 2 is nothing but minus GMN RON parallel to ROP. Similarly, we can calculate the second gain also, AV2 also the same thing, because both the MOSFETs are identical. Then the overall gain of the amplifier is nothing but average of these two, AV1 and AV2, both values are same, so the average is nothing but it is GM1 RON parallel to ROP. Okay, so another method is that this is the gain of this differential amplifier, and another method is we can use we can use the diode connected load instead of current source load. In diode connected configuration, the drain of the MOSFET is shorted with the gate, and in diode connected mode, the diode is like the drain of the MOSFET is shorted with the gate. Okay, here, and its equivalent resistance is nothing but 1 by Gm. If Gm is the transconductance of that device, then the equivalent resistance is 1 by Gm, or it is 1 by Gm parallel to its actual, the R0 value. Okay, so here also the analysis is simple. Here, the differential pair, if we consider, the load is replaced with the diode connected MOSFET. So, in half circuit analysis, if these M1, M2 are identical and M3, M4 are identical, then in half circuit analysis, I will erase all the thing. Half circuit analysis, we will consider one of the half, and this one we will replace with its equivalent resistance. Then that equivalent resistance structure become, here we will give V in 1, and here we are assuming ground, because for AC signal that this point P is virtually AC ground, and here the resistance value is 1 by Gm. Here it is a PMOS, so it is 1 by GMP, and it is parallel to RO P. Here it is VDD, and this is also nothing but it's like a common source configuration. Then we will get the output value. The Vout1 due to V in 1 is minus Gm, or that Rout value into V in, that is minus Gm1, or Gm1 you can replace it with Gmn itself, that here the MOSFET is N type, so minus Gmn, and the total resistance of this one, if we consider this in the output resistance is RON, the resistance of the total resistance of the load value become 1 by Gm3 or Gmp. Here it is Gmp parallel to RON parallel to ROP, or Gmp parallel to, here it is Gmp parallel to ROP parallel to RON itself. And then we will get the, say, V in 2 or AV2 also we will get the same value. And if we neglect the channel length modulation parameter, lambda equal to 0, if we are considering lambda equal to 0, the value of R0 and R0N and R0P we can neglect. Actually it is not neglecting, the value of R0N and R0P is infinity. So in parallel combination it's become, in this one it's become minus Gm of N into 1 by Gm of P. Or if we substitute the value of transconductance of the MOSFET, it will become mu n in terms of n type MOSFET. It is mu n COX W by L of n into ID of n, and that GMP it is root of mu n COX W by L of P into ID of P. As these two MOSFETs are connected in series, the current will be same. So these two will cancel, and mu COX will cancel. The actual differential gain we will get, it is minus root of mu n W by L of n divided by root of mu P W by L of P. This is a very important formula. From this one, if we are neglecting channel length modulation, using this diode connector configuration, we can design any differential pair, or we can design a differential amplifier with a gain whose gain can easily controlled by the dimensions of MOSFET. And we know mu n and mu p are constant, so the gain we can rewrite it as AD equal to some minus parameter k into root of W by L of n divided by W by L of P. In our university exam, they can ask to design a differential amplifier with a gain of 10. So then you can simply use this formula to design that differential amplifier. The constraint is that the value of k, usually we will take it is 3 or 4, or we can choose it is 4. Then what we need, the value of gain 10 equal to 4 into root of some x value. You can find the x. From that x, you can define the value of W by L of n and W by L of P. That ratio we need to design. That's all. We don't want to specify what is the value of W or what is the value of L. So these are the basic method to improve the gain of the differential pair. And one more is there that we will discuss. So in first case, we just replace the load with the current source. Current source is nothing but a MOSFET with a bias value, and that current source is replacing with a simply a resistor. And here in diode connected configuration, this will be the diode connected configuration. Both the case, please note that this one is PMOS. It is very important. This one is PMOS, and you need to mark the arrow in that MOSFET configuration. And the last one is differential pair with the cascoded load. Okay, in we discussed the working of cascoded load in the first module. Cascoded load, we are trying to improve the output resistance to improve the gain of the amplifier. Here also we are using a cascoded load configuration which will improve the gain of the actually it is not improving the gain. This cascoded configuration will improve the resistance of the load resistance of the circuit, and that will improve the gain of the differential pair. But there is a drawback in the circuit. When we add extra MOSFETs in the circuit, the output swing of the configuration or the output swing of that differential amplifier will decrease, because each MOSFET need at least a VTH value to maintain it is in the saturation condition. So there will be a voltage drop across that MOSFETs, and that will reduce our output swing. Okay, so we will discuss the working of this cascoded load. First we will go to the basic cascoded configuration. So this is a basic cascoded configuration of MOSFET amplifier or a common source amplifier. There we connected a biased MOSFET as the extra cascoded element. So this is nothing but it is a common gate configuration, because in small signal analysis this will be act as the ground. This will be the input to the M2, and output is taken at drain terminal VD. V out is taken at drain terminal. So here the input is at the source and input is at the gate and source is grounded. So it is a common source configuration, and in this one we given a DC bias at a gate, but it is a common gate configuration because gate is at AC ground, that source and our drain are not in AC ground. And in this analysis, in this cascode configuration, what we found or how we calculate the gain is, we try to find out the value of effective transconductance of this configuration and the output impedance of this configuration. Then the gain is AV equal to, we found that AV equal to minus GM into R out. Okay, to evaluate that, first we need to evaluate the transconductance of this device, then we need to evaluate the output resistance. To find the transconductance of the device, what we did, we short the output, the short circuit current we will calculate, short the output to ground, and we found the output current I out, and we found the value of I divided by P input will be the transconductance of that MOSFET. For that, here we grounded this one, and this is a small signal equivalent of the grounded configuration. Then these two are connected in series. Okay, this one is shorted ground. Here this MOSFET, here is this indicating the M1 and the top one indicating the M2. In M1 we need to connect the input at a gate, so input is connected, and here we neglected the channel length modulation. Actually in M2 we need to consider body effect because the base sorry not base sorry the source of the M2 is not grounded, so there must be a body effect. Here we also neglected the body effect. If the body effect is there, this will be also there, that is GM2B or GMB2 into VSB will be there. Okay, that will be also there, and VSB if we measure, that also will be equal to our source to this voltage will be there R2. Okay, here I am neglecting this one. So here it is VGS2 will be there, the VB is grounded in small signal analysis, and here it is shorted, and we need to find this current. This current is nothing but GMVGS2, and that current will flow through M1 also. So these two currents are same. Okay, these two currents are same, that is nothing but GMVGS1 will be the output current. So we will get the transconductance is nothing but GM1 itself. Okay, so here I am deleting all. So from this circuit, these currents are same, and we need to find this current I out, and I out is nothing but I out equal to GM1 VGS1. VGS1 is V in itself, so I0 by V in, the effective transconductance is nothing but GM1 itself. Okay, so we will get the effective transconductance is GM1 itself, and next we need to find its output impedance. For that we will go for this method. A test voltage is given at the load terminal, and we will evaluate the current, then Vx by Ix. So there will be a Vx will be given, and we need to calculate Ix, and we will get Vx by Ix will be the R0. While evaluating this circuit, we will get these 2 terminals are grounded. So this one is grounded means these two terminals are shorted, which is equivalent to a drain configuration, diode connected configuration. And I made a mistake, I think. With respect to it is not connected to drain, right? So it is not a diode connected configuration. If it is diode connected means it need to connect to it need to connect like this one. This must be grounded. Okay, so it is not a diode connected configuration. Here it is the gate as well as source is grounded, which is equivalent to a resistance of R0 itself, because the source is grounded. So from source to ground or drain to ground, there will be a R0 will be there. So the source is grounded means input is also grounded, so we will get only this current source will be 0, and this resistance only will be exist from drain to that ground. Okay, here if we evaluate this small signal model, this current source is 0 because input is 0, so only from drain to ground only R0 will exist. So this one we can replace with a R0 or R01. And while evaluating the effect of this one, we will get the total R out is, using the small signal model we can prove that the R out is 1 plus GM2. Now we are looking from this one, similar to our MOSFET analysis, the reflected resistance of R01 to drain of this one, R01 to drain of this one is multiplied by gain of this M2. So the gain is GM2R02, the intrinsic gain. So the gain is multiplied in R01. So the reflected gain resistance of R01 at this terminal is 1 plus GM2 R02 into R01. This formula is very important because we will apply this formula in the next derivation. So I am repeating the same. In the output impedance calculation, in the source there is a resistance R01. If we reflect that resistance to its drain, that resistance value, equivalent resistance value, is nothing but that R01 into 1 plus gain of that given amplifier. This gain here we consider only GM2 but practical case, the body effect will be there, GM2 plus GMB2 also there. So R0 is 1 plus GM2 R02, R01 plus R02. Compared to this R0, this will be a huge quantity, and this one we can neglect. We will get the effective R0 is nothing but GM2 R02 R01. Okay, so if we cascade one more configuration, or one more VB is there, M3 is there, then it become GM3 into R03 R02 R01 will be there. This is a general formula, so you can use that in the derivation of differential amplifiers. Okay, this is a method to finding the value of R0 that we did in our class. You can go through this one. Okay, so the final gain of this cascaded configuration is minus GM1 into R0, that is GM2 R02 into R01, or if all values, all MOSFETs are identical, it's become GM minus GM R0, the whole square will be there. Okay, just go through this one, and if three sections are there, it become minus GM R0, the whole cube will be there. Okay, so this will be the gain of cascoded configuration. The same we will apply in differential pair also. In differential pair, in using cascoded configuration, here arise all. Here we are adding a cascoded load here. The same we will add in both input side as well as output side. This one is for improving the gain. This also will improve. This one is for improving the output impedance. Okay. So when we evaluate how many the number of MOSFETs in the upper layer above the Vout must be equal to number of MOSFETs in the lower layer, then only we will get an equivalent MOSFET. Earlier case, in the CMOS common source amplifier, we found that the top one is a current source. If the current source in the load, its impedance is infinity. Okay, if we are taking some type of load here, the effective output resistance will be that RD. If I am connecting RD parallel to what we calculated. So if we are using some low value of resistance here, there is no meaning of this cascading. Okay, so for getting a proper output value, we need to make sure that number of cascade stage in the upper is equal to lower stage also. Okay, so here the differential pair with the cascaded load, here also we cascaded a section, and these are the loaded section in the output. When we look into this as a half circuit symmetry, these are P type and these are N type. So here it is GMP will be there, here it is GMN will be there. And just when we look from the up to down, or just we consider this is our cascaded half circuit, then we will get the effective transconductance GM is nothing but GM1 itself, because only one is connected to V input and he will provide the current to the remaining configuration. Okay, and when we evaluating the output resistance, here I am splitting with respect to this output. Here we will need to find the Rout. Rout consists of two parts, that Rn will be there for the N-type MOSFETs and Rp will be there for P-type MOSFETs. Okay, and what is the value of Rn? Rn we already calculated. Here it is M3 and M1 will be there, and the resistance are, here it is R0N, GMN in both case. Then the resistance will be approximately equal to GMN into R0N, the 1 plus GMN R0N into R0N of, when we are looking from this one, this resistance is simply R0N, and that is multiplied with this gain of this MOSFET and plus again R0N, and which we can approximate it to GMN R0N square. And we know the effective transconductance of this one is nothing but GM N itself. Okay, this will be the transconductance value. And when we consider RP, if we are looking to the upper side, this we need to look from the output terminal, then this will be connected as symbol R0P, and this is multiplied by gain of M6, so it's become 1 plus, we can write it as GM6 if you want, and R06 into R08 plus again R06 will be there, that is the resistance of this one will be there in series, so which can be approximated to GM6 is nothing but GMP into R0P the whole square. So we need to do a parallel combination of these two, and we need to multiply that with the GMN to find the actual gain. So the effective gain of that half circuit is GM1, or here it is GMN, we can use GMN into R03, R01. In textbook they given in terms of R01 and R02 itself. So GMN R0N, here is also N, here is R0N, here it is GMP R0P, R0P. So this will be the effective gain of that differential configuration. And the main drawback of this circuit is due to the presence of large number of MOSFET, there will be a limitation in output swing. Okay, so I will explain what is the limitation. So the minimum value of output is limited to VGS3 minus VTH3, VGS1 minus VTH1, and the maximum value is limited to VDD minus the threshold voltage in the upper side. Okay, so the proper operation, why it is happening, we will explain. For the proper operation of this differential pair, all the transistor M1, M2, M3, M4, all the transistor must be in saturation region. Okay, all the transistor must be in saturation region. The saturation region, our condition is the drain voltage VD must greater than VGS minus VTH. So if we consider the lower level of the output, here we got the lower level is nothing but VGS3 minus VTH3, VGS1 minus VTH1. So the lower level of output, this voltage must greater than this one, that is, if it is 0, this voltage must be greater than this voltage. Here if we write with respect to MD, VGS3 minus VTH must greater than this voltage. Okay, gate to source voltage, and this voltage must greater than this voltage VGS1. So the total voltage must be greater than VGS1 minus VTH also will be there. So the total minimum value that we can use here is sum of these two overhead voltages. Otherwise, if we drop below that, these two transistors cannot keep in the saturation region. For keeping in the saturation, drain voltage must greater than the overhead voltage. Similarly here also, if we consider from the input side, we will use this concept later also in differential op-amp also. So please go through this one. Okay, so if we consider the maximum value of this one, that maximum value, with respect to this maximum value, we know this source voltage is VDD. Okay, this one is VDD. So the maximum value such a way that this drain voltage, in case of if you are considering PMOS, it will be reverse, right? PMOS, it will be reverse. So this maximum value is such a way that to keep this M6 and M7, M8 in saturation. So the drain value, that VDS must less than VGS or VS. Oh, sorry, my mistake. VGS minus VTH value. So according to this one, this value must less than VDD minus the overhead voltage of M0, M6 and M8. Overhead voltage, V overhead we will give V overhead, that is VGS minus VTH of 6 and VGS minus VTH of 8. Or you can use VGS minus, VDD minus VTH of, V overhead of 5 and 7. That also you can use. Okay, so the maximum value is limited, and usually we are expecting the output value will vary from this. Output value will vary from 0 to VDD, but it can vary only from peak value it is there. Okay, it can vary only from some let it be 0 to VDD, but we can vary is only from this range, that is from VG 2 overhead voltage of N type, overhead of N type minus, here it is VDD minus 2 overhead voltage of P type. Okay, so ഇതാണ് അതിൻ്റെ limitation. Okay, നമ്മൾ പറഞ്ഞത് വളരെ സിമ്പിളാണ്. Just we are replacing the load with the current source and diode connected configuration. We can improve the gain. Also in using cascoded configuration, we can improve the gain of the amplifier.